All right, so in this video, what we are going to be discussing is something known as sequence notation. Now, sequence notation is going to give us a method of kind of classifying or labeling, really, I should say, things that we do in a sequence. Now, a sequence is basically a function whose domain is, positive numbers. One of the things that we're going to be doing different in a sequence is that, first of all, we're saying it's a function, but it's not saying which function it is. So a sequence can use basically any type of function that we might have seen in the past. Now, that's not to say that you're going to see a whole lot of weird functions. You're not going to see too much in the way of like radical functions or logarithmic functions, but you may occasionally see an exponential function. You may see something that is maybe a quadratic function, but most of the time they're going to be something, maybe a linear function, maybe something quadratic, maybe something to the third power. Nothing really out of this outlandish. Okay. Now, terms, that's just kind of the nomenclature of what we're going to be using to describe, I don't know, like the numbers that we're saying. Okay, so this is the first term. What's the number of the first term? So the first term might be, a 5 or something like that. All we're saying is that, okay, so here, this is a term that we're going to be looking at, and the number in this term is this. Okay. No, so we're going to be still looking at this in terms. I still recommend looking at it in terms of thinking it. Well, we have x's and we have y's. Okay, so now we might have a term and a number in a sequence. Okay, but it's still basically an x and y, and I'll kind of explain it to you as it comes up. Seeing, well, oh, that's what this is. This is x. This is y. So here, what we're using is we're going to kind of start talking about here a sub n or an. We're going to look at that in terms of saying f of x. Okay, these are essentially going to be the same thing at this point. We would say f of x if we're specifically referring to a function, or I might say, in this case, I'm going to say a sub n or an to represent, I don't know, some other function, but it could be pretty much anything we wanted to. Okay, now here, I know this thing is kind of in the way here, but it says a sequence is infinite. It never ends. Okay, well, that is kind of true. Mathematically speaking, yes, a sequence can go on forever, getting bigger and bigger and bigger and bigger forever. But this is not exactly true. Most of what we're going to be looking at are actually going to be finite sequences, because in the real world, it's really not possible for me to add up or look at an infinitely long list of numbers. So we kind of truncate it at some point and say, well, I'm only interested in the sequence from this point to this point. And so in a lot of respects, most of the things that we're going to be looking at are actually a finite sequence. Now, the sequences that we look at, they could be increasing, they could be decreasing, but mathematically speaking, most of them are going to go on forever. So at some point we have to truncate it and say, well, I'm only concerned about it from the first one to the third one or something like that. So that's why we kind of think of them as a finite sequence. All right. So here, what we have is kind of what we're going to be looking at. So again, the a of n, or a sub n, that is where we would normally see f of x as, in function notation. And we would say like 3x plus 5. Well, here we're looking at it in terms of a sequence. So the notation that we use in a sequence is a. Now, it really doesn't have to be a. It could be kind of any number. In fact, I can't think of it off the top of my head, but I'm sure I have seen at some point a different variable or a different letter besides A, but A is really the most common one that you look at when you're doing sequence notation. So here's a very common thing this asks you to do. Find the first four terms and the ninth and the 15th term. So again, there's that nomenclature, the word term. Okay, so basically it's saying is what is the output when x is 1, when x is 2, when x is 3, when x is 4, or in this case, and what is the output when n is 9 or when n is 15. That's what it's meaning when it says, okay, well, these are the terms. So if I want to know what the term is in my first iteration or the first place of the sequence, I would say a of 1 or a sub 1 is equal to 3 times 1 plus 5, which, well, that just gives you 8. So there's your first one, and you'll kind of do that for all of them. A2 or a sub 2, however you want to think of it, we'll say 3 times 2. All you're really doing is substitution to see what would the output be. So 6 plus 5 would be 11. And A3 is going to be 3 times 3 plus 5. And so 9 plus 5 gives me 14. Now, if you notice, if we were in an Algebra 1 classroom, I would kind of look at it in terms of an x and a y table. When x is 1, what is y? When x is 2, what is y? When x is 3, what is y? So in this case, we have an 8, an 11, and a 14, and you can start to see that these are increasing by 3 each time. So this is where the slope 3 over 1 comes from. So at this point, you can very much see a pattern as a linear process that for each successive number in the sequence, the term is going to increase by 3 each time. So the fourth one, you don't really need to, a of 4, you don't really have to write it out. And you can just say, oh, well, that's going to be 3 more than the last one, so that should have to be 17. And a of 5, God, I can't write to save my life today. My handwriting is terrible. I know it's not great to begin with, but a of 4 would be 17. A of 5 would be 20, and so on. So now if you wanted to, you could keep counting all the way up to the 9th or the 15th term, but quite frankly, I think it would be easier to actually do the math when you're doing them one right after another, the pattern emergence is pretty easy to count. Sometimes they pick a number that's pretty far out there that makes it really hard to count that way. So once we get to the numbers past a certain point of where we're kind of counting a whole group of them together, just substitute the number and figure out what it is mathematically. So here we'll say 3 times 9 plus 5, and so that is 27 plus 5 is 32, and then we'd say a of, what was it, 15. So I'd say 3 times 15 plus 5. Well, 3 times 15 is 45, plus 5 is 50. So the way that we might, put our answers is we would just kind of put them out as a list. We would say 8, 11, 14, 20. Oops, I missed one somewhere. I missed a 17. 17, 20, and then the two additional that we got, the 32 and the 50. So this is the terms, the list of terms that we're looking for, the first 4 terms and the 9th and the 15th one of this particular sequence. Okay, so that's pretty much it. Now here we have a sequence that is a rational function, meaning that if it was a rational function, the variable that we're looking for is in the denominator of a function, but we're also taking that same variable and putting it in the exponent position. So this is very much something that you would see when we were talking about like our exponents in the real world, where we're doing financial math, where n might be the number of times that we're compounding something in a financial formula. So same idea, find the first four terms, the 8th and the 12th. Now this is going to be a little bit harder to actually see the pattern emerge, but it's not impossible. So same concept, we're going to just really just start substituting 1, 2, 3, and 4 into the sequence or into the function, however you want to think of it. And so we'll say 1 plus 1 over 1 to the first power. Just substitute those numbers in there and see what you get. Well, 1 plus 1 over 1 is 2, and 2 to the first power is 2. So there's my first term. So now I'll say A2. So let's look at the next one in the sequence. So I would say 1 plus 1 over 2, substitute the numbers, and 2 here. So 1 plus 1/2 is 3 over 2 squared. Well, that would give me 9 over 4. Now I know you could put that one as a decimal, as like 1.5 for the fraction 3 over 2, and then 9 over 4 as a fraction is, or as a decimal, is 2.25. But I'm going to keep them as decimal, or I'm going to keep them as fractions, because a lot of times when you're doing these things, the decimal numbers are not nice decimals. So let's keep them as fractions. So next one, A of 3, and just substitute your number and simplify the expression. So we're going to say 1 plus 1 over 3 to the third power. Well, 1 plus 1/3 as a mixed fraction, or as an improper fraction, is 4 over 3 cubed. Well, 4 over 3 cubed gives me 64 over 27. And again, just type that one into your calculator and see what kind of decimal number you get. It's not going to be a very good one. So a to the 4th power, not a to the 4th power, a of 4, 1 plus 1 over 4 to the 4th power. Well, in the parentheses, 1 plus 1/4 is 5 over 4. And I'm taking that and raising it to the 4th power. And you're going to see pretty quickly these numbers start to get big because, that number in the exponent gets bigger. So 5 to the 4th power is 625, and 4 to the 4th power is 256, and that fraction doesn't simplify. So there are the first 4 terms, but now it's asking us, well, what about the 8th and the 12th term? So let's do the 8th term. Now again, looking at the numbers here, it's very difficult to discern what the pattern is, as well. Clearly the numbers are getting smaller, but how much smaller? So it's not anything to try and visualize to see what the pattern is. It's not worth it on this one. It's just better to just substitute your numbers. You'll get the answer more reliably and likely faster. So here, A in the 8th number of the sequence, the 8th term of the sequence, will be 1 plus 1 over 8 to the 8th power. Now at this point, if you combine your like terms in the parentheses, 1 plus 1 over 8 is going to be 9 over 8. And at this point, if you try to say 9 over 8 to the 8th power, or even if you just take the individual numbers, 9 to the 8th power or 8 to the 8th power, they give you something extremely big, something that is not very wieldy. The whole reason why we leave things as fractions is to avoid unwieldy decimals. Well, this works out to be a super big number with my fractions. So to keep things neat, to keep things simple, I'm going to stop right there. I'm not going to bother trying to see what 9 to the 8th power is, because it gets to be a very, very big number. And we still have a bigger one to do yet. We still have the 12th number in the sequence. So that means I'm going to raise something to the 12th power. So 1 plus 1 over 12 to the 12th power. Again, so now 1 plus 1/12 is going to be 13 over 12 in the parentheses. 13 to the 12th power is much, much bigger than 9 to the 8th power was, and we didn't try to write that out. So again, I'm going to really just stop at that point. Okay, so the numbers that we have that we're asked to identify, the four terms, the first four terms, and whatever the 8th and the 12th term are, if we put them together as a, one answer, we'd have 2, 9 over 4, 64 over 27, 6, 25 over 2, 56, and then we would have in the parentheses 9 over 8 to the 8th power, and then 13 over 12 to the 12th power. So this is kind of what we would look at as our answer. All right. So that is how we're going to be looking at a sequence, which, remember, a sequence is really just the same thing as a function, and saying, okay, well, if I want to know what the first 4 or 5 numbers are going to be, I really am just using substitution, something you've been doing since well before college algebra. You've been doing this for years and years. You're just taking the numbers, substitute it in, and see what you get. All right. So now what we're going to take a look at is here up at the top, because I understand some of these things are getting cut off at the top. It's asking you to find the indicated term. It means what would we have if 7, in this case, was, we were looking at the 7th number in the sequence. What would the term be for that? Well, it's really kind of the same thing. We're really going to just do a little bit more substitution and evaluate it and see what we get. But clearly the function that we're looking at is it's an exponential function because the variable is in the exponent. So the numbers can get really, really big fast or get really, really small fast. Now the base of the function is a number less than 1 but greater than 0, so it would be decreasing over time. So that means the bigger the number gets, the bigger the input that I use, in this case 7, the smaller my answer gets. So the answer that we're going to be looking at should be some relatively small number. So let's see what we get. So here I'm going to say A7 is equal to 3 to the times 1 over 3. That would be the base of the exponential function, and this would be 7 minus 1. All right, so let's work it out. Use your normal order of operations, see what you get here. So the 7 minus 1, that's, oops, I'm getting ahead of myself here. I'm thinking 6 for my exponent, wrote it down in my denominator. So this is 3, and this is 6 here. So for what is 1/3 to the 6th power? It's not a terribly, terribly big number. We're going to say 1/3 to the 6th power is 1 over 729. And just multiply that by 3, and I get 3 over 729, which is a pretty small number. So there we go. That is the 7th term of the sequence. And so now the last example that we see here on the screen, well, what is the 5th term of this sequence? So we'll say A sub 5 is equal to 1 over, and in parentheses here, we'll say 2 times 5 minus 1, and here I'll say 2 times 5 plus 1. So simplify each individual parenthesis first. So the one on the left, 2 times 5 is 10. 10 minus 1 gives me 9. And then 10 plus 1 gives me 11 here. So I get 1 over 99 for the 5th term of this particular sequence. All right, just basic substitution. Now, here is talking about recursive sequence. Now, you've actually seen a recursive sequence. Those of you that have been in, were in the class for the logarithms portion when we were talking about compounding interest formulas. There was a project that we did over, well, how long would it take you, and part of that project asked you, well, how long would it take you to pay off a credit card, and you had to use a recursive sequence. Now, you didn't actually do a whole lot of math with it because there was an Excel spreadsheet that kind of did the math for you. But here we're going to actually take a look and see, well, how does a recursive sequence work? So a recursive sequence is a formula or an equation that what we use is we use that to generate the next value, and whatever that value is becomes part of the equation. So to keep it in terms of the credit card analogy that we did in that interest project, you started off with a balance of $5,000. Well, that was the first term in your recursive sequence. So we would refer to that as your seed element. There you go, seed element. That's your first term. So I would have said, put that number in first into the problem and then go from there. So the function that we worked with at the time was a of n, and capital A, lowercase a, doesn't make any difference, is equal to 1 plus r over n times a n minus 1 minus p. Now remember, the n in the compounding interest formulas, that really represented the level of compounding, 12 for 12 months. The R was the interest rate that you had on your credit card. And what we're looking at here, this is kind of that sequence, that's the part of the function that really gets changed. So this, the $5,000 that we had from our credit card portion of that project, this is what we would think of as the seed element, because that's the number that we put in there first. Okay, well, we put that number in there and we see, okay, well, now what is, and I do the math and I get a new number, and whatever that new number is goes in where that 5,000 was before, and then we get a new number, and then that goes in where the 5,000 was before, and so on. And that's how a recursive sequence works. And it usually is going to be a decreasing thing over time, because you're paying something off, or you're something is breaking apart. Like I don't necessarily think like radioactive decay, but something is falling apart, or something is becoming less over time. That's what a lot of recursive sequences are used for. All right. So here we have an example of a recursive sequence. So what it's telling you here, it says A1. This is the first term that the sequence produces. First term, not term. Get an M that looks like an M. There you go. And what we want to know is, what are the first 5 terms of the sequence? Well, the first one is given to you. So the first is the 5. I don't know why we're at 5. No, 5 because the first 5 sequences. That's not where here. The first term of this particular sequence is -2, which was given to you. Okay, so that is my seed element. That is what gets put into the function the first time. So in order to find the second thing here, I'm going to say a of 2, or a sub 2, is going to be equal to the first element, because that's what the n minus 1 is. Okay, well, we're moving on to the second one. So here I'm going to say the first term, that's what I place in there. So -2 minus the 16, and here I get a -18. So here is the second term, the second number of the sequence. So now let's look at the third one. Well, that -18, now that's what gets substituted into the sequence that we have. So I'm going to say a of 3 is equal to -18 minus 16. And -18 minus 16 gives me a -34. So here's the third term of the sequence, and now that number gets substituted in order to find the fourth one. And it's just a continual process. Once I know what the new number is, I substitute that into the sequence to see what the next number is going to be. So negative 34 minus 16. Well, negative 34 minus 16 is negative 50. So there's the fourth number, and so we got one more to find. The fifth number of the sequence gets found by using the fourth number in the sequence. So I'm going to say negative 50 minus 16. So the fifth number in the sequence is going to be a negative 66. And there you go. So the first 5 terms will be negative 2, and you don't really need to put it in parentheses because I didn't put the other ones in parentheses. Negative 2, negative 18, negative 34, negative 50, and negative 66. And there we go. There's the first 5 terms of the recursive sequence. So again, a recursive sequence basically is kind of like the same thing as a sequence that we were looking at before, but the new number that I substitute comes from what I did before. Okay. Now here, same exact idea. It says find the first 5 terms of the recursive sequence. Well, what it's given it to you here, this is the first term of the sequence, and this is the second term of the sequence. And I know that because the 1 and the 2 there. So the first term in the sequence, well, it's just 1. Second, that's my 2. So now let's find the third. So I actually need the first and the second element in order to find the third one. So let's see what we get here. So let's go ahead and start plugging in our numbers. So what we're looking for is the third term of this particular sequence. So here, I'm looking for the third term. So I'm going to substitute a 3 anywhere I have an in my sequence. So I'm going to say 3 minus 1 here, and plus, and in parentheses, I'm going to, again, substitute 3 for in. So I'm going to say 3 minus 2 here, and square whatever that is. Well, the reason why I need the first and the second element for this one is because when I simplify the sub numbers here, 3 minus the subnotation, 3 minus 1 is 2. So that's why I need to know what the second element is. So C of 2 is 2. And here in the parentheses, the 3 minus the 2 is going to give me 1. So that means we want to know what is the first number, the first term. Well, the second term, again, that was given to us, that's 2, plus the first term, 1 squared. Well, 2 plus 1 squared is 3. So the third term in the sequence is a 3. So now let's find the fourth one. C of 4. Same thing. I kind of need the numbers that come before it in order to get these new numbers. So we're going to say C of n minus 1. In this case, we're looking for the fourth one. So I'm going to say 4 minus 1 to show you which one I'm looking for. Now, mentally, you can probably just go ahead and combine those and say, oh, that's going to be 3. But for demonstration, I don't want to skip that step. So here we're going to say, again, 4 minus 2, and whatever that term is, squared. Well, this is the third term, and this, when I simplify it, is the second term. So the third term, well, we figured that already. That was a 3. The second term was given to us. That's a 2. So 3 plus 2 squared is 7. So here is the fourth term in the sequence, and we have one more to do, the fifth term in the sequence. So C of 5. Again, just substitute the 5 wherever you have an in, because that's what you're looking for. So C of 5 minus 1 plus C of 5 minus 2 squared. Well, 5 minus 1, that says, well, we're looking at the fourth term of the sequence, which we just got, plus the third term of the sequence, which we previously got. Well, the fourth term of the sequence is 7. The third term of the sequence, is a 3 squared, so 7 plus 9 says that the fifth one is going to be a 16. So the first 5 terms of the sequence are going to be the 1 and the 2 that was given to me by the problem. Then the third one that we got was a 3, the fourth one that we got was a 7, and the fifth one that we got is a 16. So there are the first 5 terms of this recursive sequence. And that's pretty much it. Remember, it's same stuff that we've been doing for a long time in algebra, but we're giving it, because we're talking about a sequence or a series of something, they do have their own slightly unique vocabulary. A term is like the y numbers, the output numbers. A sequence is pretty much the same thing as a function. And so in order to find the output of a function, I just do substitution. And that's all we're doing here. We're basically just, it's called glorified substitution. That's all we're really doing. Now, we are going to be doing more with this stuff, obviously. But, you know, I wanted to make this lesson is really to introduce you to the vocabulary associated with it and a few minor operations that we'd be doing with it. So at this point, if you have any questions about anything that you saw in the presentation, make sure you write them down. Bring it to me when you come to class or in tutoring, and I'll be happy to help you with any questions that you might have. But until then, thanks for watching, and see you soon.